the language of the universe.
But I don't understand it.
Hello everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 72, where today we have another very exciting history of physics episode.
Let's go.
Very, very exciting stuff.
One of my favorite episodes to record.
For sure. It teaches us so much about, well, the history of physics and what some of these individuals, contributed to society. But this particular episode, we have one of the individuals requested quite a lot, Sir Alan Turing.
Let's go.
So that's going to be cool.
That's
going to be cool. I'm very excited about this one.
Yeah, and I'm going to be, well, I guess we're both going to be presenting, but the person that I chose, Max Planck, one of my favorite physicists, best character arcs in the history of physics that there is, just because, we love quantum mechanics here on the podcast, and
We do.
Max Planck, he's not really a protagonist in the story of quantum mechanics, but he's just that one figure that caused the entirety of physics to just melt down right before his eyes. And so we had to bring him on the history of physics today.
Yeah, I mean, I think Max Planck is a big contributor, right, to what we understand about radiation, right? A lot about light, a lot of that stuff. So also, I think I said Sir Alan Turing. I thought about it. I don't think he's a sir. So because he is and like that OBE, like the Order of the British. So he has been like awarded by the Queen, I believe, like posthumously, like long after. But I don't think it was sir. So I misspoke for that. But yeah,
is he doctor?
Podcast news. What's up?
Is he a doctor?
Alan Turing, well, mathematician, I'm assuming. Yeah, PhD, of course, from Princeton. What am I saying? Of course. What am I saying? So doctor, of course, but sir, I'm not quite sure, right? Sir, I'm not quite sure. Let's get into the news. For followers, we're sitting at 11.7. We're technically very close to 11.8 thousand Spotify followers. So get us to that 12. For those of you listening on Spotify, just go ahead and click that follow button. Why not?
And we also just hit 1,000 subscribers on YouTube.
That was big.
So thank you. Thank you very much, everybody. If you're listening to this right now and you want to check out the video version, make sure to go on YouTube. Make sure to leave a subscribe because, we're trying to get to, we're trying to match our Spotify followers.
So
that,
big goals.
Who's the stronger platform? YouTube or Spotify?
Who's the stronger platform? I like that. Are the listeners stronger or are the viewers stronger? Let's see it, you guys. Very exciting stuff. And lastly, on the news section, we have 180,000 downloads. 20 more thousand. How often do we? So for the last 30 days, we got 25,000. So in about a month, we're hitting 200. Wow.
Nice.
Thank you to everyone who continues to, download. And obviously, this would not be YouTube. This would only be our listeners. So this is also a battle kind of counted in there. But yeah, for sure. Thank you to everyone. Continues to listen.
Anyways, if you want to be mentioned on the podcast, make sure to leave a comment under this YouTube video and you might get selected to be next week's comment of the week. But for the time being, this week's comment of the week comes from Louisa. She says, I gotta say, guys, these last weeks I've been having a blast listening to you both talk about math and physics. The quarantine has separated us physically from others, and listening to your discussions makes me feel at home, in parentheses, college.
Was it the one that was made like this, like recently? Yeah. I love this one. I know I read it. I felt so nice.
So yeah, well, thank you very much for your comment. Very nice words, very kind words. There are also some other very good comments. But,
for sure, 100%.
We have to pick one. And yeah. So if you want to be next week's comment of the week, make sure to leave that comment.
Very
Anything
simple.
else? Oh yeah, congratulations!
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 We got a winner.
The giveaway winner we are giving away, well, we did the giveaway if you didn't participate. It was on Instagram. We gave away our very first piece of math and physics merch. T-shirt, the black logo, looks awesome. So yeah, the winner, Thajas. I don't know how to say the full name. I don't want to butcher the pronunciation, but
I believe she said it on one of the IGs. It was Tejasvini, and I believe I pronounced it right, and she was happy for that. So hopefully I got that on right. And again, congratulations. Obviously, thank you to everyone who participated. Right, it was like a random giveaway. I mean, whoever was in there, it was very sloppily done, right? But it was nice. It was just a fun experience that we had. So it was nice. So thank you to everyone who participated in the giveaway. But coming up soon.
All right, boom. Let's get into this podcast.
Let's get into it. Let's start. History of physics.
Max Planck.
Let's start with him.
All right. He was born in 1858 in Kiel, Germany. Okay. And I always love talking about the history of physics because, history in general is just super fascinating. But I want to put everybody here in the mindset of back in the day, in the 1800s. So forget pretty much everything you learn about, modern physics. Back in the day, it was just classical mechanics, as well as like the theory of electrodynamics by Maxwell. And that's pretty much it. You know what I mean? There was, of course there was thermodynamics and all that stuff, but...
like a lot of Newton and all that good stuff.
Yeah. But at the time, people legitimately thought that there was nothing left to discover. They said, okay, we know like how bodies move, right? Just like classical mechanics, and how planets orbit. We know about the laws of thermodynamics, electrodynamics, all of that stuff. What else is there to discover?
Quite a lot.
Yeah, it turns out it's quite a lot.
Yeah.
But if you think about it, they didn't have, of course, the technology that we have today. And so it makes sense, right? You can kind of explain everything that you do on a daily basis somewhat. So yeah, when you go into physics, you just learn what they have, and then they kind of tell you, well, this is all that there is to know.
Because I guess at that time already, so much had already been done that they were like, okay, at this point we're just learning. Like even school nowadays, you're not really discovering anything. You're just learning stuff that's already been done. Yeah. So there's no real curiosity. There's no real inquisitiveness. Unfortunately, that's lost. Which is why they thought they're just done.
Well, right? I forget who said this, but somebody said at the time that the only thing left in physics was to get more and more accuracy in the experiments, which, due to quantum mechanics and all that stuff, we realized that there's actually a limit to how accurate you can get. But that was the mindset at the time. We just need better tools, better measurements, and we can just, move on from there. But, I also wanted to say that there were some like loose ends in the physics world, but most people thought it was just a matter of like not discovery, but just kind of tying those loose ends into the theories that they already had at the time. But cue in Max Planck, who was just working in his corner of physics, right? He was dealing with a little bit of thermodynamics, some radiation, right? And turns out that there was actually a very big problem in the radiation world. So first of all, I know we've talked about this before, but let's just talk about black bodies. So a black body is something that absorbs all of the electromagnetic radiation that is pointed towards it, and also emits, right?
Yeah.
And it's called a black body not because it's black, but because the color black, right, absorbs all the light, as opposed to, white that reflects.
And it doesn't reflect.
all
Exactly.
the light.
It doesn't reflect anything.
Exactly. So we have black bodies, and there's something called black body radiation, which in theory, before Max Planck, well, technically the statement I'm about to say still applies, but so a black body emits and absorbs all wavelengths of light, or not just light, but electromagnetic radiation. Sorry. And essentially what they had at the time was that this radiation, of course, can be plotted as a spectrum. The issue was that at very short wavelengths, so high frequency, high energy radiation, the graph just blows up. And so essentially what you would think, of course this wasn't true, but by looking at the electromagnetic spectrum, the emission spectrum, you would think that a black body would just instantly release all of its energy, and its temperature would go to absolute zero instantly because of this like infinite energy emission. Of course, this is not true. So this was called the ultraviolet catastrophe.
Ooh.
Because there's just this huge hole where it's like, of course this is not what happens. There's not infinite energy. This is just not possible. And so Max Planck was dealing in this area of physics, and first of all, let me just say that the what am I trying to say here? The emission spectrum was actually derived from the second law of thermodynamics. And Max Planck tried to do the same thing and still come up with a reasonable solution that actually fit the data. Because we had the data. They were able to collect the emission spectrums of black bodies, and they saw that it did not coincide with what they had theoretically. So they knew what the curve looked like, and it kind of looked like a bell curve that was skewed a little bit over to the left side,
like a skewed normal distribution.
Yeah. But sorry.
Video just went off.
Yeah, the video just got off.
Oh, switch cameras.
1 sec.
Sorry. All the viewers are like, what is happening?
Okay. So Max Planck actually decided to postulate, or just assume, in his derivation of this spectrum, he assumed that electromagnetic radiation could only be absorbed and emitted in quantized energy packets. What a ridiculous assumption.
How do you even think of that?
Just
random.
It's so out of the box. Nowadays, with everything that we have, we look back and we're like, okay, makes sense.
Well, obviously.
But
I hate how people say that. Well, obviously it's this.
Yeah.
Well, not
obviously.
to them.
Yeah.
It was really not that obvious, man. It was really not that obvious.
Yeah. So he assumed that these they're called quanta, these energy packets, was true for any material. And this has a lot to do with when you heat up an object and it glows at a certain color.
Yeah.
The assumption that of quanta, energy quanta, has a lot to do with that, and I guess we can come back to it in a second.
Because the whole black body radiation spectrum relies on thermal radiation, right? Like that's how every body, like even we emit radiation, just that we emit it in the infrared. Because all of our particles are technically vibrating, right? Which is how we get to a certain temperature. If we were just completely stationary, we would be at absolute zero, which would make no sense, obviously. So we're all vibrating at a certain temperature. And because of the fact that we are at that temperature, we give off a certain radiation, and that was described. Maybe you can continue with Planck's law and stuff like that.
Mm-hmm.
Right.
So this idea, this assumption, is actually what triggered the entire quantum revolution. Because, of course, you publish this idea, this assumption, and people go nuts. You know, they say, well, you can't just assume things without proof. But I did a little bit of research, of course, before the podcast. And this was actually just by intuition that Max Planck did this.
Oh, really?
He said he said
this guy.
if I assume this, I can actually derive an equation that perfectly
This guy's nuts.
describes the black body spectrum. And so he said, well, maybe there's some truth to this lucky guess. And he stuck to it. Of course, if assuming something that, you know, can't be proven wrong at the time, if somebody says, okay, you can only have these quantized packets of energy, you can't really say, well, okay, here's a microscope, you can see this is not true. You can't. And by assuming that, it actually perfectly describes the exact problem that you're trying to tackle. And so he ran with it, and he stuck to it, and in his equations and everything he was doing at the time, it made perfect sense. And it actually ended up explaining a lot of the holes that there were in physics. But little did he know that the holes that he was trying to fill would just tear apart everything that they
that
knew.
we knew about physics. Oh my.
So
let's stop it there before you want to go any deeper, or do you want to talk more about him?
No, I did actually.
Okay, continue.
So, Max Planck was considered the grandfather of quantum theory, and his solution that he came up with was actually in the 1900s. Okay, and this discovery of the quanta actually earned him the Nobel Prize in Physics in 1918. Okay, here's something that's interesting. The discovery of these energy quanta actually explains, it's kind of the backbone of Einstein's Nobel Prize winning experiment, the photoelectric effect. But Einstein's hypothesis of the light quanta, which is actually known today as photons, the force-carrying particle of the electromagnetic force. It was actually rejected initially by Planck, because let's remember, or I guess I never even stated this, but Planck was a very traditional guy. He was not here to shake up the game, shake up the entire physics world. He believed, well, it's not a matter of believing, but he really stuck to the things that they had at the time, like Maxwell's theory of electrodynamics. And in that theory, light is an electromagnetic wave. And so he was a wave guy, you know what I mean? And so when Einstein came along and said, light is actually a particle, a photon, and it kind of goes hand in hand with Maxwell's ideas that energy can only be exchanged in quantized packets. He was unwilling to just throw away Maxwell's ideas. And here's a quote. He said that the theory of light would be thrown back not by decades, but by centuries into the age of Christian Huygens, when he dared to fight against the mighty emission theory of Isaac Newton. Remember, guys, back in the day, Isaac Newton proposed that light was a particle, and Christian Huygens was one of the guys who said, no, I think it's a wave. He had a lot to do with the double slit experiment, which is pretty good evidence that light is a wave. Today we know that it's a little bit of both, but when you have these great scientists debating over these ideas, of course, the most popular scientist is going to win.
Sure.
At the time of Max Planck, he's like, okay, well, Maxwell kind of hit the nail right on the head. There's no way I'm going to throw away my ideas about light and just go back all the way into the 1700s where they were debating the same topic.
And then the whole wave particle came later, right?
Yeah. The wave particle was just a little bit after. Actually, Max Planck would have been alive for the wave particle
Totally, yeah, right.
kind of merging of the two ideas.
Interesting.
And here's one last quote that I have.
Why not?
He says, and this is a very popular quote, he says that a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it.
Oh my.
And it's such a good quote because think about this. You believe something. You hold it very close to your heart. There's no way that somebody's going to come in and say, you know what? You're wrong. And you just go, oh, okay. All right. And, maybe there are some cases where scientists do convert their ideas. But exactly what Max Planck said, what happens is that time takes over, It doesn't matter who thinks what is right. It's just eventually those people will die. The new generation will take over with, fresh blank canvases. And the correct ideas or the seemingly correct ideas for that generation will just triumph.
Mm-hmm.
So, yeah.
Yeah, time definitely plays an integral role in all of this. Like, who knows? I mean, Newton, for example, still like 400 or 500 years later, like 400 years later, we're still using a lot of his philosophies, right? So who knows? I mean, because Planck's radiation law, Planck's radiation law and stuff like that, maybe we can dive a little deeper into it later, but a lot of that, can be similar to, Newtonian mechanics that kind of lives on forever, because these black bodies are not going to stop living, right? Everything is basically not a perfect, but everything is basically a refined black body. So you can think about it that way. So it applies to almost everything, right? So who knows? Maybe Planck becomes the name of the... Yeah, you never know, right?
I mean, he's already...
Yeah, valid.
He's already
valid.
up there.
Already very, very well known. Valid. Moving on. Or unless you have anything to say about Planck. You good? All right. Let's move on to Alan Turing. Alan Turing was a British mathematician, cryptographer, computer scientist. Well, when computers weren't even a thing back then. And he basically invented the modern day computer. And he basically invented the idea of artificial intelligence. And he was also an integral part in winning the Second World War, right? Or the whole thing that took place. For those of you that have seen the Imitation Game, you may know a little bit about who Alan Turing is. And I'm going to mention how funny that is because the movie is named after something completely different that he has done. And it's just nothing about the actual movie itself. Anyways, we'll get into that. But so he's done some pretty notable things in his life, right? So first off, like he graduated from Cambridge, mathematics degree. I think like he knew he wanted to do mathematics from the get-go itself. Huge fan of cryptography. And then he graduated Princeton, PhD in mathematics itself. And I believe a lot of people like close to him, and you always read these biographies and stuff like that. And a lot of people said that he's kind of that very awkward person, likes to be by himself, kind of likes that. And again, if you see the movie, I think a lot of this will make sense. It's kind of nice how they portray his personal life in that movie, and it's kind of realistic. But anyways, let's talk about his actual contributions, right? That's what's most important. So the first, no, this is definitely chronological, right? Yeah. So I'm just going to list like the three biggest things that he's done. Number one, the Turing Machine. The Turing Machine is basically what we call the computer. The modern day computer is based on the fundamental logic developed by the Turing machine. The second thing that he's done, very notably, in the Second World War itself, is crack the Enigma machine. Now, the Enigma, or the Enigma code, or whatever it was called, was basically the Germans' encryption machine, way to send code between different locations. So what they would do is they would type in a code, it would send it to another Enigma machine by Morse code, and then it would decrypt it on the other machine. Now, obviously, the thing is, this was the most crazy thing to crack, right? This had been like uncrackable. There's like a crazy number of combinations to try to actually crack it. And the craziest thing, every day, the whole thing resets. The whole actual encryption resets. So there's a new page every single day. And again, like I'm just thinking about the movie as I'm saying this, because the movie is a lot about based on this. So whoever's watched it, you will notice a lot of things that I'm saying very similar to what he's doing. And, you know, every day, day after day, like they're staying up and boom, the bell rings and they couldn't figure it out. And there's a new code already, you know, so that's like a big problem. And what Alan Turing did is that he made the machine called the bombe, the BOMBE. Again, not quite sure the naming or the nomenclature behind it, but that basically cracked the Enigma machine. And I want to talk a little bit about that too, like really crazy achievement. And then finally, AI. This guy basically invented AI, man. This guy basically invented the modern day understanding of artificial intelligence by something known as the Turing test. So, before we get into anything, let's talk about the modern day computer. When we run a program on a computer, what it's basically doing, right? And as we like, and if anyone's taken like a basic computer science course, or you know, a lot of our listeners, maybe some into tech, so know that everything runs on binary code, right? Everything is either a 1 or a 0. Everything can be represented in terms of a 1 or a 0. And depending on how many or how much memory you have, you can store more 1s and 0s, or you can store less 1s and 0s. And a program, and this is where he came up with the Turing machine, and this is exact a Turing machine. Imagine a tape. An infinite tape of 1s and 0s. Now, obviously, this is a hypothetical idea, but obviously shorten the tape and you can make this a finite program. But just hear me out here with the logic. There's an infinite tape with 1s and 0s. And there's like a kind of like a read-write head. You know, on the hard drives, like you have those read-write heads. You can think about it like that. And for every piece of tape, there is some code that basically tells this read-write head what to do. So it'll go left. It'll replace that with something else. It can only do two things. It can either move left and right, because remember, it's a one-dimensional tape. It can move left and right, or it can change. It can read the information on the current cell, or it can change the information on the current cell. So it can change a 0 to a 1 or a 1 to a 0. That's basically the idea. And every single program that we think of today can be broken down into a Turing machine, into a program that can be run on a Turing machine, right? Now, obviously, these are very simplistic examples to start, but let me give you the idea behind why would you even want something like this, right? This guy, I don't even know if I mentioned, he was born in 1912, so a little before the First World War. He was kind of, as I mentioned, big part of the Second World War. So, well, why does he even need this? So for hundreds of years, right, ever since like the 1700s or something like that, there were people called computers. And what they would do is they would sit and compute things. So their job in a lot of these, I guess not really companies or whatever they were really back then that needed to compute, I guess for any research project or whatever, there would be people, and this is, again, back in the day, all women, that would be computers. They would literally be called computers. And on a job application, you could actually put down that you were a computer. And I really like that. And that's a little funny. Anyway, so that was the traditional definition of the computer. And then Alan Turing thinks, hey, what if I can mechanize the process of computing? So instead of adding two numbers by hand, you're adding it through some program.
Real quick though,
Yeah.
Just a little piece of information
Of
for the
course.
history of computer science. Ada Lovelace was a woman, okay? She
Okay.
was the first person to publish an algorithm intended to be used on a computer. And guess what? This was before computers were even invented.
Wait, when was this? When was this? What year was this?
This was in the... Wait, I don't actually have the date.
Okay, could just continue what exactly she did.
That's all I had to say. Like, she wrote an algorithm.
That basically ran on the Turing machine?
No. I don't know what they actually... Like, it worked. I don't know what they ran it on, but it was probably the Turing machine.
The first
since
computer
it was the
algorithm
very
is
first
what you're
one.
trying to say, though.
Yeah, I'm saying the
It
very
was written
first...
by okay, amazing. Amazing.
It was written by a woman before computers. How
Damn.
do you...
That's pretty intense. That's pretty intense. So yeah, I mean, basically, this is a modern day computer, right? Like, just telling this read writer head what to do is basically the definition of a modern day computer.
Yeah,
and
this was in 1840, by the way.
1840. Okay, the Turing machine was made in 1936. I had it right there. 1936 is when the Turing machine was invented. So definitely a little bit later. 100%. Wait, so that means this was like... Oh, so the Enigma was actually... Yeah. So the Enigma and the Turing machine were happening at the same time, which obviously makes sense. So that's basically the foundation of the Turing machine and a little bit of the computer. It's really cool that lady had, written the first programmable or program. But basically, if you think about it, adding two numbers can be thought of as a program. And that can be done on this sheet, on this infinite tape. Now, obviously, that's a very simple program, but anything you really think of can be broken down into a Turing machine, right? And that is where I'm assuming the computer got its name from, right? Because it was computing things. That's basically the whole thing, right? And it basically is just following these instructions, this code that was given to it in the first place, right? And it basically just goes by that, and after it's done, it either halts or it doesn't. Now, here's the big thing. Now, here's where it gets crazy. I want to talk about a few things with Alan Turing. He's really insane, but let's talk about this first. Is there any problem that a computer cannot solve?
Yes.
Which was you're saying, yes, there is a problem that the computer cannot solve. So a big part of after inventing this modern day programmable computer, quote unquote, well, the question was very simple. Let me back it up actually a little bit. Let me back it up. In I'm missing the exact year, but some time ago, David Hilbert, very, very, very famous guy. He basically invented everything. Like, everything of modern day mathematics was him. Hilbert he was the king, the god of mathematics, basically. And he had these set of problems where he was trying to see if mathematics was a perfect model of the world. And he had a few problems here and there, and he's like, oh, if this is true, then mathematics. If this is true. So he had these 3-4 problems, right? I believe it was 3 problems. And I believe like 1 or 2 were solved, 1 or 2 were disproved by a student, by Gödel. A lot of people may recognize that name. But I don't want to talk about that. I want to talk about the decision problem that Hilbert posed. One of these fundamental questions about mathematics was very simple, or not very simple, but this was the question. Can we know, or can we determine, if every statement can be proven or disproven? So, basically, what that easier way to say it is, given enough time, will we be able to determine if a given statement is true or false? Or not true or false, is provable or disprovable? That's the idea behind the decision problem. Alan Turing comes in the picture. He's like, I'm going to change up this wording a little bit to satisfy my definition of a computer. So he says, is there any program that can determine if said program will halt or not halt. Now, for those of you maybe not familiar with a lot of computer, what does that mean? So when you write a piece of code, while true, execute something and it just executes forever, it's an infinite loop. That piece of code will not halt. That means that piece of code will go on forever and ever and ever and ever and will simply not loop. And something like this, and the question was, well, if you give this to a Turing, if you give this to a Turing machine, it'll just continue to do something over and over and over and over again. It's not halting. Now, a program will halt. Obviously, the contrary example to this will be if the program actually does end up stopping. So that's your idea of halting and not halting. And Alan Turing had converted the decision problem. Now, he's also a mathematician, so don't only think that he's just doing this theoretically. This is very deeply integrated in mathematics. It's just that I'm going to be skipping out a lot of that just to get to the understanding of what exactly he did.
But
right?
Hold on, how are those two statements equivalent?
Okay, so Hilbert asks again, can we know if a statement can be proved or disproved? And Turing asks, can we know if a program will stop? That means it has been executed. That means it was successful, quote, proved, or not stopped. Cannot be proved. Get it?
Get that,
so that's basically the idea behind converting that to now what is known as the halting problem. And this is a very, very, very famous problem that almost every single first or second year or any year's computer science student will be aware of, right? Or at least knows a little bit about. And this is how he phrases the problem. And this was his solution to the problem. Now, this is a little confusing, so bear with me. And Parker, you can be my witness there, like the first time hearing it, because I know I even told Parker I'm not going to tell you. I'm going to wait for the podcast. So you tell me your raw, reaction. So before we continue into the crazy halting problem, I do want to bring up a very, how do I say this, friendly program to us. Brilliant. Now, if you liked any of this computer science stuff that I was talking about, in particular with logic and understanding basic computer science, the halting problem, the decision problem, logic, basics of that, you can go check out brilliant.org. It's a crazy website. It offers insane courses that basically talk about and teach you all of these varying concepts. Computer science, a little bit of quantum mechanics, that is a little advanced, but a little bit of that also included. And this month, they actually included new interactive courses with their logic courses, with their math courses. So you can actually play around with it, actually visually learn. So there's a big advantage. So go check out brilliant.org/MPP to sign up.
And the first 200 listeners to sign up a premium membership on brilliant.org using our code will get 20% off their membership. So go ahead, click that link or type it, brilliant.org/MPP. Boom.
Boom. That's it. So let's continue. A halting problem. So this is crazy, okay? This is going to be insane. So just everyone listening, everyone viewing, just chill. The halting problem. This was Alan Turing's answer to the decision problem. And he basically said, can every statement be proven? Or do we know if this can be true? And the answer is no. We don't know. And this is, right? Yeah, exactly. We don't know. And this was his explanation. Take a program that can do two things. Think of it like a function. It takes in a program and then it does something. Now, what it does is two things. Step one, it will check if the program halts or does not halt. So obviously for this, we assume that we can make a program that will determine if a given program would halt or not halt. So we are assuming the statement to be true. Valid? Valid, right? So we're assuming that this kind of machine can be made, and then we're going to take it from there. So let's say we can make such a program. So the first thing this program will do, it has two things it'll do. The first thing it'll do is check if the given program will halt or not halt. Very, very straightforward. Then, if the program will halt, it will spit out yes. And if it will not halt, it will spit out no. Now, here's the thing. The second thing it does is a little confusing. So again, just bear with my logic here. If the program halts, that means it stops, and it says yes, the second part of this program will loop infinitely. That means it will not halt. But if the given program does halt, sorry. If the given program does not halt, that means the given program will loop infinitely. The secondary program will halt. So here's the program once again. Let me make sure this makes sense. It takes in a program. If that will loop infinitely, the second part of this program will stop. But if this program will not loop infinitely, the second part of this program will loop infinitely. And that's basically this whole program. Now, Turing said this. What if we put this whole program into itself? Follow the logic. Follow the logic.
Oh.
The program, let's say, does not halt. Right? That means it goes on infinitely. Right? It does not halt. Then the next part of the program will stop immediately. But then if it stops, that means it did halt. So this should go on infinitely. But if it goes on infinitely, then this should not halt. Then this should stop.
So wait, hold on.
Does that make sense?
Is he gonna like infinitely feed the program into itself?
No, the conclusion is that this is inherently a mathematical paradox. That you cannot make a program that can determine if said program will halt or not halt. Basically concluding that the decision problem was solved and is untrue.
But wait, hold on. Why can't
ask your questions?
Okay. Why can't you just say that the program that determines if a program will halt or not halt?
Yeah.
There's only one part to it, and it either says yes or no, and then there you go. There's your program.
No, but you're trying to prove that statement, man. Come on. You're trying to prove if that statement is true. You're assuming that there is a program that exists like that, and you're trying to see, well, would that work? So what he did is he created a counterexample. He put the second instrument right next to it, right? And do the exact opposite of what this guy does, basically. Yeah. And then send that whole thing into itself.
I get it.
Right? So it's crazy. And this is basically how he answered the halting problem and the decision problem, which was one of his greatest feats. And again, it was massive because basically it proves that a computer cannot find the answer to every question. And that's a little scary if you think about it.
But hold on, I have another question for you.
Go for it.
If you assume that it's true, here's the problem. Okay, so the statement you're trying to prove is a there exists statement, right? Because you're trying to find one program that can determine, right?
Well, no. The statement is every. The statement is every program has a provable or disprovable solution. And we would know that. Can we determine that?
No. I'm saying Alan Turing's
counterexample was one program. Yeah, I mean, it was give this whole program into itself.
Listen, his general idea was to show that, like, there exists one program that can, in fact, determine whether every program that you feed into it was gonna halt or not halt, right? So
no, he said the opposite. He said there is this program that basically negates this statement, which means you cannot determine that every of these work.
But listen, that's how he proved it, was by assuming it's true, showing a contradiction.
Yeah, but
Okay.
the statement is every is true. So even if you show one doesn't work, you immediately contradict the statement.
But listen to what I'm saying. Because he proposed
Bro, this is
an
a really famous
idea.
thing. Are you really trying to argue with
No,
me?
no,
Like, I'm
no.
not really
I'm
the
just
best
trying to-
arguer for this,
I'm
but like
trying
this is
to
like a big
understand
thing
it.
that he's done.
I'm trying
But yeah,
to
continue.
understand it.
Yeah, of course.
Because he proposed one example of a machine that can determine if it halts or doesn't halt. But what if there's another example of a machine that can do that?
Okay,
And
okay.
it doesn't contradict.
Okay. Let me put this again. Mathematical terms. You have a statement where every statement must be this. You prove there is one statement that does not do this. Is the statement not false?
Yeah, you're right.
That's exactly it, right? That's
But I
exactly it.
still, I don't
No,
know.
I get what you mean, but the point was that no, this cannot be done because again, you can find a counterexample which negates the whole every part of the statement. And
So
again,
hold
this is a very I have skipped over so much math obviously because it's a lot,
Yeah.
like, you know what I mean? So there's a lot of math that goes into this that I'm just explaining the theory behind, but believe me, like, it does work out and it's crazy. And it's freaking crazy. So
Okay,
that's
wait,
the halting problem.
I
Yeah.
think you said it wrong though.
What did I say?
I think
Did I mess up?
the statement is for all programs there exists a solution stating whether it halts or does not halt, right?
Is that not what I said? For
No.
all programs,
So
there's just, yeah, that's what I said. That for every program, we can determine if it halts or doesn't halt, which is, right?
okay.
Right?
Sure. Yeah.
It's a little
sure.
interesting. It's a little interesting.
Yeah,
Definitely in the
yeah.
comments below if you want to ask something, like, for sure. It's definitely a very interesting problem.
Yeah.
And again, it just really shows you how some people just think just outside of the whole box, you know, like they're not even there. They're not even there. Like, so I just really like the way he describes it. And that's the halting problem. That's one of his really crazy things. Let's continue on to some of his other crazy things that he did. The Enigma Machine. Now, this is something that he cracked in World War II. And big props to him. Because basically, he was able to successfully decipher the code sent from and to German bases, right? Which was a big thing. So, little history here. I think I already went through it, but a little more history. Germany basically used this machine for all of its, for all sending and receiving any kind of messages. It used to send it via Morse code, and then it used to decrypt it based on the machine. Now, their job in the best way possible, where Alan Turing was working like with the British government, this was like a highly secretive job to the point where even after he broke it, literally 20 years after he died, like he had died, and still nobody knew that he had done that. He couldn't say it because it was
Whoa.
under the Official Secrets Act of Britain. So he couldn't even say anything. And 20 years after he died, he was actually then like, okay, he did this. So I mean, it's
Wow.
kind of sad, like the way it went, and he died for a really sad reason. I'm gonna get into that, but anyways, let's get into the Enigma, right? So what he did is he was again a big fan of cryptography, right? Which is basically trying to decode and decipher a lot of these encrypted messages. So he made the machine, as I mentioned previously, called a bomb. And it's a pretty complicated machine, which basically, again, feeds in messages and it tries to decipher something. The problem with this machine, again, for those of you who have seen the movie, for a long amount of time, it just wouldn't stop. It would continue going forever and ever and ever because it would take so long to decode the message. However, and again, this is also in the movie. I'm just remembering the whole movie as I'm saying this. But then one day, they thought, hey, a lot of these messages have similar words. Like every 11 a.m., every day at 11 a.m., the Germans would say the weather report. So it would have the weather. It would have the word is. It would have one, depending on the time. Stuff like that. And they also noticed that every letter that they would write was written as a word and not as a letter. So that also gave them combinations to look for. Especially with given times of the day, they would look for different combinations. And eventually, they cracked the Enigma machine using Turing's machine. And it was crazy because they were basically going to like shut down the project, like defund it. He was going to be kicked out, and then he got back on. It was this whole thing. And then basically it finally worked. And it was super, super cool and super sad because he wasn't really, this was one of his biggest accomplishments, and it wasn't even known, right? Until he had died like 20 years later. And the saddest thing, so he was an openly homosexual man. And obviously at that time, it was not very, very, very nice. I believe he was charged by the court for indecent acts or something, like some crazy like that. And he actually committed suicide because of the amount of hate and stuff that he was receiving. And there are some theories that it's not suicide, accidental, stuff like that. But it was, like, I think there was some cyanide poisoning. So it's closely linked to that. Anyways, really sad stuff on Turing's side for why he passed away. Just not the best time for him to live in. But clearly, I mean, he improved it by a lot. Enigma Machine, this guy broke it. So that's really cool. That was his second accomplishment I wanted to talk about. And then finally, I want to talk about AI, right? His final paper, or not final, but his most notorious final paper. In 1950, he released a paper on computations where he posed this thing called the Turing test, or the Imitation Game. You see that? So this is a completely different thing. So the Imitation Game is actually something based on the Turing test, which has nothing to do with him solving the Enigma machine. So again, it's just weird. It's weirdly named. Anyways, so what is the Imitation Game? Now this is really cool. Listen up. Imitation Game is simple. There are 3 rooms. One of them has a computer. One of them has a person. One of them has a judge who is also a human. Right? So there are 2 humans, 1 computer. Both the humans, well, there's 1 human and there's 1 judge who's basically judging this whole scenario. And they're all in different rooms. Here's the test. Everything is done by text, right? Because they're in different rooms, right? So you're basically typing everything. And the question is simple. After a 5-minute period, or any amount of period, the game was for 5 minutes, can the judge accurately tell the difference between the computer and the human? That was the test. That was the imitation game.
Hold on, but
basically, if the computer
what kind of what kind of computer are we talking about?
So obviously, the idea is if a given computer can pass the Turing test, we can call it intelligent. And that was his whole introduction of artificial intelligence into the world today, right? But now let me tell you a little bit of the controversy. There is a little bit of a controversy with this, right? There's a lot of it because what kind of questions can the judge ask? Is it just yes or no questions? Because then can she ask mathematical questions? Then obviously the human would be stumped. So what kind? And then there was the whole debate on, well, what is intelligence? How are we defining intelligence? So he said a very simple answer. There's some amount of behavior that humans do that are not intelligent. Quite a lot these days. And there's some amount of behavior that humans don't do that are very intelligent. The middle ground is where you want to test them. And that was the idea of the Turing test. Now, because it's so vague and so, it could be this, could be that, any question that you really want, because it's so vague, there can't really be too much backlash, right? Because it's such a vague thing to do. It's nothing like that's exact. It's just, hey, ask your questions. And after 5 minutes, if 70% of the time you cannot determine the difference between them, that computer has passed the Turing test. And I believe till date, there have been, I think like 1 or 2 off chances, but I don't believe any computer has successfully fully passed the Turing test. But again, it's all about what, and now modern day researchers kind of negate this. They're like, that's not really what we're going towards anymore, because do we really want to make a computer like a human? No, we want to make it better than a human. So we don't want to compare. So that was his idea. But again, the fundamentals of Alan Turing creating that idea of intelligence, the very first idea of computer intelligence and comparing them, that's what's essential, you know?
And a great video that I recommend everybody to go listen to. I guess I'll link it in the description. It's by Cold Fusion on YouTube, and it's about GPT-3. Do you know about GPT-3?
I have heard of that abbreviation somewhere.
It's essentially, it's like a virtual machine, I think, that's artificially intelligent.
Yeah,
And
I've heard of something like this.
apparently it's the most advanced like artificial intelligent thing that is like, I think it's not yet public domain or whatever, but it's like some people were able to test it and everything, and there are so many things you can do. So many
Damn.
One example is that you can give it any topic and it will spit out an essay on that topic.
Really?
That's like
Damn.
high level,
That's
high
nice.
like intelligence, like very well formulated and all that stuff. Like, listen, if high school students get a hold of this machine, then it's over. You know what I mean? Like, oh, write an essay on Shakespeare. You know?
Damn, it would just like use
Like-
all the knowledge ever.
Yeah.
Because he's access to the internet. The internet in these days
Yeah.
is it's insane. It's insane. Like you see those movies about your robot, you know, connected to the internet and hacks all your devices. To be honest, that's totally possible. Like, that's completely possible given a sufficiently good programmer has programmed that particular device.
Yeah.
Like, you hear so many times about people getting hacked, and it's not even crazy to assume so on the same Wi-Fi network if everyone's there. Anyways, I'm just giving like hypotheticals. But let me give you an example of a Turing machine, or not a Turing machine, but machines that are trying to get the Turing test passed. In 2018 or 2018, I believe, it was Google had an event where they premiered for the very first time Google Duplex. And what Google Duplex did in front of 7,000 people live is booked a haircut appointment.
Oh, I remember that.
You remember that, right? I think a lot of
Yeah.
people remember this one. This went viral when this happened. A computer perfectly booked a haircut appointment. I believe there was a language barrier in that particular conversation. There was a little there was a little back and forth, but it continued that conversation. Now, obviously, we're not there, but that's the idea of where we're going. Just giving you an example of different machines that are trying to copy it, or at least not copy, but trying to pass that test. Let me give you another example. Captcha. Now, Captcha is actually a reverse Turing test. Because if you think about it, Captcha is a computer trying to tell if a human is actually a human. Right? In a Turing test, it's the human telling the computer if the computer is human. So you know what I mean? So this is so a Captcha is the opposite. And what does it stand for? I have it right here. It's kind of funny. Completely automated public Turing test to tell computers and humans apart. That's Captcha. That's basically what Captcha stands for, right? And it, by definition, is a reverse Turing test.
Yeah. Wait one sec. My mic is just messed up.
Oh, there it is. I think it
it's
sounds
back
better.
again.
Yeah.
Okay.
So basically, you know, different machines, different automations, different programs like that are kind of on its way to reach that level. And artificial intelligence, you know, is always a question about when we're going to reach that. But these are just, you know, some of his, I think these are just insane. I mean, every time we go through a history of physics, I think me and I believe Parker as well, just have an amazing realization about, you know, the amount of work, the amount of difficulty, the amount of struggle that some of these guys had to go through to get the basic knowledge that's in our head. The basic knowledge that we know about computer programs. Like, how easy is it to write hello world, print hello world for those computer science nerds? It's a big joke there, but so simple. But not in 1920, not in 1930, right? It was the craziest thing if you could do something like that, even close, remotely, like mirroring a computer or a human computer at that time was amazing.
I mean, that's why science evolves and
It's
continues.
so amazing
right?
how it does as well. Really appreciating how it evolves and what it evolves into. And that's what we should really appreciate the knowledge in our head, man. I'm telling you, a lot of us don't do that. We're like, oh, this is Newton's laws of gravity. So simple. You know, who doesn't know this? But like,
we learn about
was
quantum
amazing.
mechanics in grade 12.
like who
Like-
even...
Yeah.
Like, who even... Einstein took like 10 years to figure out the concepts of general relativity, and it's explained concisely in a couple of years, 2 to 3 years, you're already fluent with general relativity and more. So it's amazing the level at which we've come today, all because of, the sacrifices, the work that all of these people have done in the past. And that really gives you true appreciation for science, for physics, hence the history of physics.
So let us know in the comments or on Instagram at math.physics.podcast who we should do next on the history of physics. I remember,
I have seen your comment. If you're listening to this episode, the one who replied or commented, and a lot of people liked on the fact that we wanted to do a magnetism episode, the part 2 to the electricity episode. It's coming, but don't hold off on it. It's coming. It's going to come, of course, 100%. But just because sometimes, we need to give a little bit of a break. We have some ideas. We have some different topics to go through. So we're just trying to give a little bit of a break between the electricity and the magnetism, to really entice those guys. So that's basically the idea. So hopefully just stay tuned and it'll come on for sure.
So I hope you enjoyed this episode. Make sure to follow wherever you're listening to us. Go over to YouTube, leave a comment, maybe subscribe. Maybe for sure subscribe. Who knows?
Hit that like button though. Why don't just smash that like button? Check out our clips. We have clips. I know our schedule has been really messed up lately. We've been having a whole revamp of who's doing it and who's doing what. So there's been a little bit of a problem with the clips lately. I know some of you guys are understanding. I posted it on the story the other day. A lot of you responded, so thank you for that. And just bear with us a little bit in the coming weeks. But we're gonna get back on for sure.
Alrighty.
Oh, and the crazy news. 1 month, Parker and I moving in together.
Oh, yeah.
So 4 or 5 episodes?
We didn't
mention that. Yeah,
we mentioned it on the live.
Yeah, I think. Oh, yes. So for those that are listening to the podcast, Parker and I are going to be moving in together next month, downtown Toronto, obviously because U of T. So every episode is going to be we're going to be together. So that's going to be really cool.
Yeah.
So it's going to kind of change our podcast a little bit for the better, so very excited for that.
All right, well, thank you for listening.
I don't think so.
No,
I think we're
good. This has been episode number 72 of the Math and Physics podcast. I'm your host, Parker,
and I'm Ray. We will see you soon.
Bye, guys.
See ya.